I wanted to say a few things about the definitions of oxidation and reduction that aren't always covered everywhere else. So we know that oxidation is the loss of electrons and reduction is the gain of electrons. And first of all, I want to acknowledge that these definitions are not necessarily the most intuitive or the easy to remember things at first glance. This is where mnemonics are really helpful. Two of my favorites for oxidation and reduction are oil rig. So you can think about what that stands for. Oxidation is loss, reduction is gain. And that's snappy, but it has two fundamental problems. One is that it uses fossil fuels, and we're supposed to be transitioning away from fossil fuels. The second is it doesn't actually tell you what's being lost and what's being gained. Is it electrons, protons, charge? Who knows? So for those reasons, I prefer the mnemonic like this. Leo, the lion, goes grr. And this would stand for loss of electrons is oxidation, gain of electrons is reduction. That reminds us specifically what's being lost and gained. It's electrons, which do everything in chemistry for us. So I think that's a little bit better in terms of mnemonic. The other hook that I use sometimes to remember what's going on, oxidation or reduction, is the term reduction itself. That sounds like something should be going down. What is it that's going down? Well, GR tells us reduction is not a reduction in electrons, it's actually a gain in electrons. But what do we know about electrons? They're negatively charged. That means whenever we're gaining electrons, we're actually losing charge or going down, more negative in charge. So when I think about counting charge, tabulating charge to determine what's happening, if the charge is going down, then that's reduction because electrons are being gained. The other question that comes up a lot with oxidation and reduction is where these terms came from in the first place. They actually go all the way back to the 1700s, not long after scientists first started experimenting with oxygen after it was discovered, and particularly looking at oxygen's reactions with metals, what we often call oxidation just in everyday life. So here's an example, the rusting of iron in oxygen. We can analyze what's going on here using oxidation states. Both iron and oxygen start out as pure elements, oxidation states of 0. They end as this ionic compound, oxygen with its usual -2, making iron +2, which is not unexpected for a transition metal. Iron has gone from 0 to +2. That's a gain in charge. And since electrons are negative, that means it must have been losing electrons. What is loss of electrons? Loss of electrons, Leo, is oxidation. So iron was getting oxidized. And I chose this reaction for a reason. How did we accomplish that oxidation? We reacted iron with oxygen. Oxygen accomplished the oxidation for us. The term oxidation started out from looking at reactions like this as a description of what oxygen did to things, particularly metals. Now, we now know a little bit more chemistry, and you know the periodic table. And oxygen sits fairly close to the upper right-hand corner of the periodic table. We know about periodic trends, and we know what this upper right corner of the periodic table is like. These are our elements that are the most electronegative, the most electron hoggy, the ones that most want to pull electrons to themselves in covalent bonds or to form negative ions, and therefore pull electrons away from other things. If oxygen shows up, it's highly likely to steal your electrons. In fact, the only element that's going to be better than that is fluorine. So oxygen was known at the time that these reactions were first studied, so oxygen gets tagged with this identity. It's the electron stealer. If you were oxidized, you were going to be losing your electrons because oxygen's taking them. They didn't know about electrons in the 1700s, but we still carry on their term. So reduction. Reduction is the reverse of this, and where did that term come from? It would have been much nicer if they had just called it deoxidation. Well, let's pretend we are scientists in the 1700s. We study oxidation, we think we know that, and then we try to run that reaction in reverse. So I'm going to flip that reaction around. Now we have rust, iron oxide, going back to form solid iron metal, and oxygen gas is getting liberated into the air. Now, we're just starting to understand gases because it's the late 1700s, but what can we easily measure and understand? We can look at the solid. We can look at that rust becoming iron again, and we can measure and weigh that on our scales. And when we do that, when the solid goes from being iron oxide to losing the oxygen and being just iron, its mass is going to go down. Its mass is going to get reduced. So the reverse of this oxidation process resulted in a reduction in mass. And now we've generalized that term now that we know about electrons. Now electrons are getting given back to the metal to liberate the oxygen. So reduction for us is now the gain of electrons. The final thing I want to say about this terminology comes from the fact that oxidation and reduction always have to complement each other. If one thing is gaining electrons, something else has to be losing electrons to be the source of those electrons. You can't have oxidation without reduction. You can't have reduction without oxidation. So in this reaction, if we look at what happened to oxygen, oxygen was itself reduced. It went down in charge, it gained electrons. Doing that enabled iron's loss of electrons. For iron to lose those electrons, they had to have somewhere to go, and that ended up being oxygen. You can think of oxygen in this case as the enabler of oxidation, the agent of oxidation. It makes oxidation happen, but it isn't actually oxidized itself. In fact, it's reduced. So calling it an agent of oxidation, an oxidizing agent, is kind of like calling a travel agent. This agent is something that helps something happen, but doesn't undergo that process itself. An oxidizing agent is not oxidized. A travel agent does not travel with you. But both of them facilitate the thing they're agents for. So oxygen, in this case, is reduced, but it enables iron's oxidation. We call it the oxidizing agent, and sometimes these terms get shortened to oxidant, or you may see oxidizer, particularly on labels and chemical packaging. Similarly, iron is oxidized. Iron lost electrons, which enabled oxygen to gain them. It enabled oxygen's reduction. So iron is the reducing agent, which also gets shortened in terminology to reductant or reducer.